Okay, so I thought that for our next problem, we would work on another clearing an obstacle type problem. This will probably be the last one for a bit. How do we clear a rectangle? So let's imagine we have a rectangle of height b and width a, and our goal is to project our projectile from the origin with the minimum possible speed to just barely clear this rectangle. I also want to know what is the launch angle required. So what are the launch speed and what's the launch angle? Also, I guess, how far away are we from that side of the rectangle to just barely clear this? So first, let's get the speed. The easiest way to do this is actually fall back on stuff we've already worked out before. Let's move the whole problem up to this corner. So the minimum launch speed will correspond to the minimum speed at this corner point to just barely clear the range, which is the width of the rectangle. In other words, if I have my projectile launched with some speed I'll call v from this corner, and I want it to make it to the opposite corner just barely with minimal speed, notice that that distance is just a. But we have previously worked out what is the range of a projectile that is launched on level ground. As a reminder, here is our equation for calculating the range of a projectile. If I want this to be minimal speed, then I want v to be as small as possible, but still give us the same range, and the range here, of course, is just a, the width of this rectangle. Well, the minimal speed to do that will be when sine of 2 theta is maximum. After all, the product of v squared and sine 2 theta have to equal a constant, so minimal v means maximal sine 2 theta, and sine 2 theta takes its maximum when the argument is 90, meaning theta is 45 degrees. So we've already worked out that you get maximal range for a given speed at a 45-degree launch angle. Now we're just inverting that and saying the minimum speed needed to clear a given range is also 45-degree launch angle. So that tells us immediately that this angle, say here, should be a 45-degree angle. And it also tells us that a, the width, should equal v squared over g times the sine of 2 times 45, but that's sine of 90, which is 1. So that instantly gives us that v squared is ga, or ag. Remember, a is not an acceleration here, it's the width. Now, that's not my final answer because that's the speed, minimum speed at the corner, but I can quickly get what the minimum launch speed has to be by using conservation of energy, or even just 1D kinematics. Notice that v naught squared by conservation of energy is just going to be v squared plus 2gh, the height. Well, the height difference there is b. So, substituting in what we just found, we find that the minimum launch speed will be g times, well, here's an a that comes from this v squared, and then I'll have 2b. All right, so that's our first result. It tells us the minimum launch speed, take the square root if you want, to barely clear this object. Now let's try to turn to finding that launch angle. Okay, so for this part, we're going to use two things that we've worked out previously. First, our good old trajectory equation. So for a projectile launched from the origin, this is its trajectory. Notice it's quadratic in x, and it depends, interestingly, on the launch angle. I've gone ahead and changed our notation to theta naught for the launch angle at the origin because I want to save this theta for something else. And we usually write a secant squared here, but let's leave it in terms of tangent. The other thing we're going to use is we're going to use a result we recently showed, which is that the slope of a secant of a parabola is actually the average of the slopes of its tangents at 2 points. So in this case, if we were to label that on this diagram, I'm going to draw a little triangle right here, and that angle will be the angle I call phi. So notice that the projectile is launched at an angle above this, theta naught, which then curves over Phi is just the straight line angle measure between my launch point and the corner of this rectangle. Now, unfortunately, there is one extra unknown that we don't have available to us, which is how far away are we starting from this side of the rectangle? Let's call that distance x naught. So now what we want to do is try to eliminate some of the information here and calculate the launch angle and how far away we are. So let's start by using our trajectory equation and noting that the height at the corner of the rectangle is just b. But of course, we don't know the position of the edge of the rectangle. Okay, so this is a bit complicated. It does have some unfortunate commonalities of squares, of tangents, and stuff like that. We're hoping that that'll be simplified. We do have a simplification, though, that we previously found. So we will be using that for our minimum launch speed down here to clean things up a bit. Let's turn now to this one. This tells us that this secant, this chord of this parabola, has a slope which is halfway between the slopes at its start and end. In other words, the two tangents. It's the average, the arithmetic mean of those two slopes. Now, tangent of phi is pretty easily written down from that triangle. We know it's opposite over adjacent, so that's b over x naught. The theta naught, we don't know. That's what we're trying to find. But the angle that this makes at the end, we do know. We've already figured out that that is an angle of 45 degrees. And the tangent of 45 degrees is 1. So this equation actually does let us simplify quite a bit. So now I have these two equations with two unknowns, x naught and theta naught. How are we going to eliminate one for the other? Well, let's see. Okay, let's go ahead and solve for tan theta naught and plug it in here and here. Yeah, it'll be a little messy, but I think it'll be a little easier than solving for x naught because we would end up with a binomial in the denominator, and that's a little uglier. So solving this for tan theta naught, we'll be able to plug it in to our previous equation. So let's see, how would we do that? Multiply by 2 and subtract 1, right? Okay, there's our expression for tan theta naught. Let's sub that in here in these two tan theta naughts, and while we're at it, I'll go ahead and plug in our result we got earlier for the minimum speed. Okay, again, it is a little messy, but such is life. I'll go ahead and cancel out these g's, that's kind of nice. And then I'll distribute in this x naught. I will also square out this binomial and then distribute in this x naught squared. That should get all of the x naughts out of the denominators. So let's do that before we get to the next piece. There's our first simplification. I'll go ahead and leave this in the denominator for now. When I distribute this x naught squared, notice that the binomial squared will have a negative 1 squared at the end, which will be a 1, plus a 1, which is a 2. And I'll push the x naught squared in. Then I will also have the square of this first term, which will be a 4b squared over x naught squared. When I multiply by the x naught squared, that'll clear out the x naught. And then finally, I'll have that cross term, which will be twice negative 2b over x naught. Multiplying by x naught squared will give me a single power of x naught. Okay, let's do some more simplifications. Notice that I can cancel this down. There is a 2 in all three of these, which I can cancel partially here. These come down to 2's. And then it is probably best to just clear denominators here and multiply by the a plus 2b. Okay, let's bring this up to the top and we'll finish by solving for x naught. Okay, so I'm hanging on to our little equation we solved for tan theta naught. Once we've got x naught, we'll be able to finish that. But now we have to solve this for x naught. Now, you can see it's a quadratic, but let's keep going algebraically, see if maybe it gets a little simpler. So expanding out to the right-hand side, product of binomials will have ab minus ax naught plus 2b squared minus 2bx naught. And then I'll distribute the negative through all of those. And we do see that there are some simplifications. The 2b squared and negative 2b squared cancel. The negative 2bx naught and the positive 2bx naught cancel. That's nice. And then moving things around and just putting it in sort of a standard quadratic form, we'll have a nice quadratic equation to solve for x naught. Let's just go ahead and use the quadratic formula. I'll leave it in a plus or minus, but we'll check only one of them is going to make sense for now. We'll have a negative a, that's our b term, sorry for the confusion there, plus or minus square root, the linear term squared, minus 4 times the leading term of 1 times the last term, which will become a positive, all over 2 times 1, the leading term. And we can see that the way we've drawn this out, x naught really should be a positive number. It's to the right, it's in the first quadrant. The whole rectangle was drawn in the first quadrant. So I don't want the subtraction sign here, because then I have negative. Negative is definitely to the left somewhere, which wouldn't make any sense. So I'll just take the positive and maybe rewrite it slightly, factoring out an a. All I've done here is pull out the a squared from inside. That'll give me a 4b over a left behind. There's a positive sign there, so I'll just rewrite that first term at the end, and I'll pull an a over 2 out of everything just to give us a common dimension to work with. So there it is. That is the location of the front of the box. It's how far away we should fire from this rectangle so that we can have this minimal trajectory. Now we just have to plug that in for x naught and get our tan theta naught. Plugging it in is actually a little bit irritating because, well, you've got this big messy radical sort of binomial thing in the denominator. However, well, let's do the algebra. Fine. So we have 2b over x naught. I'm going to write this. Yeah, sure. But if we multiply this first term on the numerator and denominator by the radical conjugate, so I'm going to multiply the numerator by negative 1 minus the square root, and the denominator by, I guess I'll put a 10, the same thing, we'll see that things will clean up a little bit. When I multiply the denominator out, first of all, I guess I'll pull this fraction up here. I'll just write this as 4b over a in the numerator. The denominator, by virtue of the conjugate, will have a minus 1. Minus 1 is a 1. A 1 times the root and a minus 1 times the root. Those cross terms cancel. That's why we're using the conjugate. And then the radical times the radical subtracted. So the radical goes away. The numerator, unfortunately, still has this messiness, but it'll simplify in a sec. And then don't forget there's still this minus 1 hanging off the end, which we haven't yet dealt with. Okay, let's bring this to the top and we'll finish the algebra there. Okay, I've literally just transcribed exactly what we had at the bottom of the last piece. Now we'll do the algebra to simplify this out. Notice 1 minus 1 cancels. I have a negative sign. That negative sign can actually cancel both of those down to positives. Notice I now just have a 4b over a in the denominator. That's it. That's all that's left. And that exactly cancels with the 4b over a in the numerator. So I'm left with a 1 from this guy plus this square root. That's still there. And then a minus 1 on the end. Well, of course, the 1 and the -1 completely cancel. And we're left with a very nice final formula for the tangent of this angle, √1 plus 4b over a. And that gives us our launch angle at this particular location with this particular speed to just barely clear this rectangle with minimal speed. QED.